Let us try to understand a thing or two about significant figures. And let me start by giving you an example which will help us understand the significance of significant figures, as to why should we study significant figures and why should we develop an understanding of significant figures. Let us say we have a class of 25 students and we are measuring the average height of the class, right? In that case, the simple calculation that we will do, a simple method that we'll follow is we'll measure the height of all the students, and then we will get, we'll add that up. So sigma hi, where h is height of each student and I is equal to 1 to 25. And then this entire thing, this summation of all the heights will be divided by 25. Right? And if you do this calculation on a calculator, once you punch in these values, the calculator may show up something like this, some 170, say for example 171.24698 probably, right, centimeter. Of course the calculator will not show the unit, but I'm writing here the unit as, and I'm taking this as the average value. So this is what the calculator will show up, right? And now if you report to somebody that the average height of the class is 171.24698 centimeter, I'm sure you'll understand that we cannot accept this as the height, because this will imply, if I give this particular value as the average value, this will imply that we have measured the height of the students to an accuracy of 5 decimal places. I can see here 5 decimal places, right? Which is not true, obviously, right? We have not measured the height to an accuracy of 5 decimal places. So in such a case, what we will do is we'll round this off and we'll say the average height is 171.2 centimeter, or maybe if 171.3 centimeter. Right? When we communicate this, what we are saying is that we have measured the height to an accuracy of 1 decimal place, right? And therefore we say that the significant digits in this particular height are 4. 1, 2, 3, 4. Right? Here it would again be 4. Whereas if we had reported this as the average height, what we would say the significant digits are 1, 2, 3, 4, 5, 6, 7, 8. 8 significant digits, which indicates the accuracy of measurement. And quite obviously, this is not true. I hope with this example you have got some idea as to why we should worry about significant digits. So whenever we are reporting any value, any measurement, we need to be clear about the significant digits involved in that particular measurement. Let's move ahead. There are certain rules of thumb which we generally follow when we want to find out the significant figures in a number or in any measurement. The first rule of thumb that we follow is all non-zero digits are significant. So whenever you have any measurement, then all the non-zero digits are significant. For example, if I measure length as 3.12 centimeter, right? Here all the digits are, here these 3 digits are non-zero, therefore the significant digits in this case are 3. Right? Rule number 2, it says that all leading zeros are not significant. They're not significant. Let me explain. Let us say we have measured this length as 3.12 centimeter. Now, if I report this in meters, then I will write this reading as 0.312 meter. Right? Now, if somebody looks at these, right, there are 4 digits over here, and somebody may say that the number of significant digits here is 4, whereas actually in the measurement there are only 3 digits. Right? This 0 has come because of change of unit. It has not come because of the measurement, and therefore we say that this 0 is not significant. This particular 0, and this is an example of a leading 0. The zeros which come immediately after the decimal point are called as leading zeros. For example, another example is 0.0042, say for example kilometers. Right? So these 2 zeros which have come immediately after the decimal point are known as leading zeros, and they are not significant because they do not come because out of measurement. They come because of your changing unit from one to another. Third rule of thumb that we follow is all sandwiched zeros. All sandwiched zeros. Although there is no word like sandwiched maybe in English, but we're going to call them sandwich zeros. All sandwich zeros are significant. Right? Okay. Example. Say for example, we have done a measurement like 602.3 meters, right? Now this 0, right, is sandwiched between two non-zero numbers. This is significant because this has come out of measurement. It has not come because of change of unit. Right? Another example is, for example, 0.0204 kilometers. Right? In this case, this 0, which is there between two non-zero digits, is a sandwich zeros and it is significant. But this 0, which is the leading 0, is not significant. So in this case, I'll say the number of significant digits is 3. Right? Whereas in this case, right, I'll take the number of significant digits as 4. Right? So this is what we mean by sandwich zero. Zeros between any two non-zero numbers. The fourth rule that we follow is of trailing zeros, right? Trailing zeros. In this, there are two possibilities. The trailing zero could be in a number with decimal point or no decimal point. For example, you have a number, if you have a measurement like 6.2300 centimeter. Right? This is an example of a trailing zero because they come at the end of the number. And there is a decimal, the number has a decimal point. So this is the type that we are talking about. There we could have trailing zeros without decimal points. For example, 3,200 kilograms. Right? So these are trailing zeros without decimal point. Now we have different rules that we use to understand this. I'll do that immediately in the next video because otherwise the video will become too long. What I'll do in this video is quickly talk about one more rule of thumb for this, and that is pure numbers. That is, do not change sigfigs. Right? For example, if I have measured radius as 2.02 meter, right? So the number of significant digits here is 3. Now, if I calculate diameter, I will be multiplying 2 with 2.02. Right? So when I multiply these two, I'll get the answer as 4.04 meter. Right? The number of significant digits here are taken as 3. Right? It is not that this multiplication or division of a pure number changes the significant digits. Right? And that is because pure numbers, we say that they have infinite accuracy. They have infinite accuracy, and the simple reason is because they are not measurements. The number is 2. The number cannot become, this number cannot become 2.1 or 2.01 or 1.99. This is going to remain 2, and therefore we say that they have infinite accuracy, and we say that they do not, numbers do not change the significant figures in a given measurement. Right? Last rule that I want to talk about is that, which we have already discussed in the video, but I will quickly mention this: change of units does not change sigfigs. Right? As we saw in an example earlier, let me go back to that page. Here we took this example of 3.112 centimeter. When we converted it into 0.3012 meter, so when we change the units, the number of significant digits remain the same, 3 here and 3 here. So when you change a measurement from one unit to another unit, there is no change in the significant figures. Okay, I'll stop over here, and in the next video, a short video that I'll do on trailing zeros, and I'll talk about decimal and no decimal point numbers. Thank you. In continuation of the previous video on significant figures, in this video we will talk about trailing zeros. As I told you in the previous video, that there are two possibilities that exist. We may have a decimal point in the number or no decimal point. Right? And let us take an example. With decimal point, we may have a situation like 2.300 centimeter. Right? Now, if I look at this, these two zeros are significant. Right? They are significant because they communicate to us that these two zeros have been put because of measurement, meaning that the measurement could have been 2.301 or could have been 2.320. Right? So these two numbers indicate that the accuracy of measurement is of 3 decimal places, and hence in such a case the trailing zeros are significant. Right? So in this case, decimal point, trailing zeros are significant. When we do not have a decimal point, so let us take an example. Let us say somebody tells that the measurement of particular mass is 3,200 kg. Now, just by looking at the numbers, we cannot say that the significant figures are 4. Because we need more information. Let me explain. 3,200 kg is the mass of an object. Now I need to know the scale on which it has been measured. For example, the scale could have been like this: 3,100, 3,200, or 3,300 kg, and the reading could have been 3,200 kg. There is the second possibility is that the scale could have been 3,190, 3,200, 3,210, right? And the reading would be 3,200. There's also a possibility that the scale could have been 3,199, 3,200, and 3,201 kg. Right? Of course, all scales are in kilograms. So I don't know which scale has been used. Right? Here we have measured it with an accuracy of 100 kg. Here we have measured with an accuracy of 10 kg, and here with an accuracy of 1 kg. So just by looking at the number 3,200, I don't know whether the accuracy level is 100, 10, or 1. So I need more information on that. So if I want to communicate, or if I want to show that I have measured with 100 kg accuracy or 10 kg accuracy or 1 kg accuracy, what we do is we represent this in the scientific notation. Meaning that if 100 kg is the accuracy level, we will write it as 3.2 into 10 raised to 3 kilogram. In this case, we will write as 3.20 into 10 raised to 3 kilogram. And here we will write it as 3.200 into 10 raised to 3 kilogram. Mathematically speaking, all the three numbers are same, right? But from a physics perspective, from a accuracy perspective, they are different. What this shows is that the accuracy over here is 100 kg. How? Because you have one digit after the decimal. So if I take 0.1 into 10 raised to 3, I get 100 kg. Here we have got two numbers. We have accuracies of two decimal places. So if I take 0.01 into 10 raised to 3, I'll get as 10. Here, three decimal places. So 0.001 into 10 raised to 3 will give me 1 kg. So if we use this particular notation, we will be able to clearly represent the accuracy with which the measurement has been made, right? And from this we can say the number of significant digits here are 2, here 3, and here 4, right? So if somebody gives us this particular value of mass, 3,200 kg, there is a possibility that the number of significant digits could be 2, 3, or 4, depending upon the accuracy level with which it has been measured. So it is always good that whenever we have trailing zeros in a number, we represent it in scientific notation so that we are able to communicate the accuracy with which the measurement has been made, and then we are able to identify exactly the number of significant figures. Right? Right. With this, I'm coming to the end of this particular video. Just a final point before I wind up is that one of the purposes, or one of the main purposes of significant figures is to avoid. One of the main purposes to avoid over-representing. Again, this is not a word that you come across in English, but to communicate this particular point, over-representing the accuracy of measurement. That is the purpose of significant figures. So what we do is we avoid over-representing the accuracy of measurement, and the person who is to whom those measurements are being reported knows exactly as to what is the measurement, what is the accuracy with which the measurement has been done. Right. Thank you.